talk about two empirical methods for measuring adaptation. Repetition is very common. I'll be talking mostly about words and variant forms of the words like plurals, synonyms, and so on. But what I hope I say should generalize to other things like ngrams. I'm going to explicitly try to do my best to avoid talking about ngrams because they're obviously the best constraints, and I want to see if I can get some other constraints that might be useful. Adaptive language models are developed mostly for speech recognition, and I'll refer to Fred's secondary source review of cache models, and I'm going to make a distinction between what I call additive and case-based models. By an additive model, what I have in mind is that you have the cache from which you build a local model somehow, and then you have your long-term global statistics, and you combine them in some additive fashion. And I'm thinking in this case, lambda is sort of a constant. It doesn't depend on the words. It doesn't depend on whether the word's in the cache or whatever. By case-based, what I mean is that I have the same two kinds of probability models, but now I'm going to separate out one case if it's in the cache and another case if it isn't, and I'll have these lambdas which might include what the words are and things like that. And so this, and what I'm going to conclude is I think the same thing that Fred concluded in this discussion, that this is better than that. These models were introduced for I think at least two purposes. One is topic change and the other is repetition. I'm going to focus on repetition, but what I think I'm going to say should also apply to the topic change case. Now, by the topic change case, what I have in mind is that the language model was trained on one kind of domain, say news, and it's going to be tested on another, like medical reports. That is, the user is going to use this speech recognition device on a domain that's maybe not the same as the training material. And you might want somehow the language model to figure that out and correct. Now, I'm not going to talk about that so much, but what I am going to talk about is the repetition. So if a document mentions an unusual word like Noriega once, then the odds are that it might well mention him again, more than if it didn't mention him. And that's what I want to focus on. Now, so the intuition here is that if a word like Noriega has been mentioned recently, then the probability of that word and its variant forms or neighbors, let me be a little fuzzy by what I mean by that, should go way up. And many other words should go down a little bit in order to compensate. So I'm going to refer to the first clause as positive adaptation and the second clause as negative adaptation. And I'm going to say that I expect that positive adaptation is much bigger than the prior, and that the prior is just a little bit bigger than negative adaptation in general. This pattern we're going to show is really huge. It's like orders of magnitude. Whereas this one is smaller. It's factors of 2 or maybe an order of magnitude, but it's still something. That is, it depends on what words are involved. It'll be stronger for content words, like good words for information retrieval, technical terms. And it'll be weaker for function words, cliches, common first names. But the same pattern will hold in all cases. So here's an old slide I've used for other purposes. But the Brown Corpus, which was collected at Brown University in the 60s when Kennedy was the President of the United States, had 500 documents in it. And this shows, and they were broken up by genre. So you had some news and some fiction and some technical abstracts and religion and so on. And within the news, there was international news and local news. And what I show here is the number of times Kennedy was mentioned in each document. And the odd thing is that he was mentioned oodles of times in the news and never in fiction. All right? So this is something we would like to account for. And even a not terribly contentful word like said.
Of course, things have now changed, right? Now he's in fiction and not in news.
No, he's back in the news, as we'll see. But he's really back in the news. Okay. You know, the family that can't go away. Even the word said, which is big in fiction and big in the press, is not so big in religion and really unusual in technical writing and abstracts. And so here's the previous figure about said. And this is the same figure, just plotted a different way. In this case, what I did is to show that there were a whole bunch of documents that didn't use said at all, and a few documents that used said 30 or more times. And you see everything in between. And that a Poisson just doesn't describe this. Now, in previous work with Bill Gale and Slavokats independently, we've tried to come up with parametric methods to fit this distribution. Negative binomials, and Slava has an even more interesting description. What I'm going to do in this talk is to try to approach this problem of measuring adaptation totally non-parametrically. I'm not going to assume any kind of parametric distribution to fit this, and I just want to ask the empirical questions of how big is positive and negative adaptation, and what does it depend on? And what is the shape? And more interesting, what it doesn't depend on. Now, recent ACO work that you probably know of, they looked at the word peace and noticed that it was more common in some genres, international news, and less common in some others, like sports. And they were interested in a speech recognition application of what's the relative likelihood of the word X in this context being one kind of piece as opposed to another kind of piece. The intuition is that in this context, the likelihood ratio should go up beyond the prior. So what they did is they clustered the documents into roughly 100 topics, and they computed a separate language model for each topic, and then adjusted the probabilities correctly. Now, what we're going to do is to replace the clustering with nearest neighbors in an information retrieval sense. And what this will do is to produce, instead of 100 topics, we'll get many, many more topics. In our case, D choose K, where D is the number of documents in the library. And also what I want to do is to replace the independence assumptions, the implicit independence assumptions, with a non-parametric model. So I'm going to introduce two methods for estimating adaptation. This is the first one. What I'm going to do is to split each document in the training corpus into two equal pieces. The first half of the document I'll refer to as the history, and the second half of the document I'll refer to as the test. And the task is, given the first half of the document, given the history, do your best job of predicting the rest. And I'm going to approach this by just calculating a contingency table. So in 1990, the AP News, the word hostages appeared 638 times in both the history and the test, and 505 times in the history but not the test, and 557 times in the test and not the history, and 77,000 times in neither. And then given this contingency table, which I'll just write this way, A, B, C, D, we can define a few interesting things. D, which is the number of documents, is just the sum of all the cells. Document frequency, which is a quantity that's used a lot in information retrieval, which I'll refer to later, it's the number of documents in which this word occurs at least once. That's just A plus B plus C. The prior probability of being in the test is A plus C over D. And then these are the two quantities I'm really interested in. This is the positive adaptation and the negative adaptation. The positive adaptation is what's the chance of being in the test given that you were in the history. And negative adaptation is what's the chance of being in the test given you weren't in the history. And these are straightforwardly determinable from this. We'll get to later some issues about how to smooth, because for a less common word, I can't just use the observations. But let me skip that for now. Hostages is such a common word in this domain that it's pretty straightforward. So what we see is the pattern that I mentioned before. The adaptation is much, much larger than the prior, orders of magnitude bigger. And it's quite consistent over different years of the AP News. It's stunningly large. That is, more than half of the documents that mention hostages once in the history will mention them somewhere in the test. Whereas only 1.5% of the documents will mention hostages at all. You might have thought this would be like 1.5% squared. It just isn't. The negative adaptation is within a factor of 2, sort of the prior. So I'm saying the positive adaptation is orders of magnitude bigger, and the negative adaptation is a factor of 2 smaller. In this discussion, I'll consider things like less than an order of magnitude as being tiny, and more than a couple of orders of magnitude as being big. And I'm not really going to try to get factors of 2. Now, I also want to say that it's lexical, so that Kennedy and accept happen to have about the same prior in this corpus in each of these years of the AP. But Kennedy has much more positive adaptation and much more negative adaptation than accept does. So that I think of this as like Kennedy, you might want to say, is manic, that it has huge highs and huge lows, whereas function words are kind of stable. Whatever they do, it kind of doesn't depend on any hidden variables like what's the document about. Even said, which is about as common in this as for and said has more highs and much more lows. So that is, this is a factor of 2 lower, whereas this isn't a factor of 2 lower. Generally, the positive adaptation is a big deal, and the negative adaptation is sort of a little deal. But for the when you're right up against the top of this, you can see there's more movement on the negative adaptation than the positive. So this is another argument. Here. This is another argument that adaptation is lexical. What I did here is I show a bunch of words like Aristide, Escobar, Noriega, hostages. These are major cities around the world: London, Moscow, Tokyo, Paris. And now you're getting into months of the year and days of the week. Washington gets stuck in here. Washington is kind of a function word in this domain. And then down here you get your real function words like under, before, after. So this axis here is the ratio of positive adaptation to the prior, and this axis is the ratio of, this is the same thing in another year of the AP News. And what I'm trying to say here is that if it's bigger, if this ratio is big in one year, it'll be big in another year. If it's little in one year, it'll be little in another year. And this line is the A equals B line, which does a pretty good job of describing it. So that whatever this property is that distinguishes Escobar, Noriega from before and under, it's pretty stable one year to another. So the positive adaptation is huge for Escobar. The negative adaptation is huge. For these guys, it's less of each, where less is like less than a factor of 2. Normally in this, we do like to do better than factors of 2, but now these are many of the same words. Oh gosh, how are we going to get this on the screen? So here's the ratio of positive adaptation to the prior as before. Here's the ratio of the prior to negative adaptation. And the point here is that this ratio of the positive adaptation is 2 or 3 orders of magnitude, whereas the negative adaptation is less than an order of magnitude, even for words like Noriega and Escobar and Aristide. Down in here, I'm going to zoom in on this region, because if I printed the words down in here, it would be too messy a slide. So the next slide will show you that region. Down in here, you can see some of the major cities: Paris, Tokyo, Moscow, London. This dimension away from the origin is content. So it's content in that direction, either up that way or out this way. And this is sort of little content down in there. So your function words have little content. Washington has fairly little content. First names like George have little content. Your months are over here. Your days of the week are up there. you can sort of see that there's some kind of clustering in this space by sort of semantic types, classes. And this is an argument that, again, the same argument I'm going to keep making in different ways, that your good keywords for information retrieval have orders of magnitude in this dimension and more than a factor of 2 in that dimension. Whereas down here, your first names, which aren't nearly as good keywords, are less than an order of magnitude here and less than a factor of 2 there. Right? So there's a real difference between how much you have adaptation depending on the word and the word type. Now I'll just show in tabular form, and the postscript is, I think, floating around here so you can look at this in more detail. But you can see there's remarkable consistency across these cities and across years of the AP News about what the prior is and how much the positive adaptation is and how much the negative adaptation is. And the thing I want to reinforce is that this is orders of magnitude. It's not a little effect, right? Now, I gave this talk, a practice version of this talk, to some visitors from Japan, and they had mentioned a problem that's a little different than information retrieval, which is how to build a Japanese keyboard. So what they do is they type in a phonetic alphabet, and then they get a menu that lists the kanji characters that they might have had in mind. And the menu orders the choices using this adaptation so that the choices that you've selected recently will be moved to the top of the menu over all other issues. And this, I think, is suggesting why that makes some sense. Here are days of the week, and the same kind of thing you can notice here. Here, the positive adaptation isn't as big as we had, but it's still, if the first half of the document mentions Monday, the odds are 1 in 4 documents, the last half will also mention Monday. And whereas the odds of a document mentioning Monday at all are much less. And the negative adaptation is nearly a factor of 2. And here's a few months. Same kind of thing. The months aren't quite as strong as the days of the week, but there's still a strong effect. And then this is that difference before between these very good keywords and these lousy keywords. The very good keywords, the odds go up, in Aristide's case, huge. This is so huge that I worry that there's some smoothing problems. But just many orders of magnitude difference. Whereas your common first names, this is still huge, but not as huge. And function words show much, much less. Here, instead of orders of magnitude, we have maybe a factor of 2. And quite a bit consistency. So let's talk about smoothing. The problem is that all of these counts and ratios of these counts become unstable when the counts are small. And the standard solutions are good Turing and deleted interpolation. I'll use deleted interpolation. And the general setting for deleted interpolation, or for good Turing, is that you let R be an observed count of something, typically the frequency of a word, but I'm going to try to move to those cells. Let R star be our best estimate of R in another corpus of the same size, everything else being as equal as possible. I'll use another year of the AP News. Split the training corpus into 2 halves. I'll use 2 years of the AP. Use the first half to count R for all the objects, say all the frequencies of all the words in the vocabulary. Use these counts to group objects into bins. So the rth bin contains all and only the words with frequency R in the first half. Then let n sub r denote the size of this rth bin. And use the second half of the training corpus to compute c sub r, that is the aggregate frequency of all the words in the rth bin. And then I'll set R star equal to the ratio of C sub R over N sub R. And then the 2 halves of the training corpus or the test corpus have different sizes. then I'll need to scale R star, but I'll ignore that. The sizes of these AP Corp are pretty comparable. Now, how do we generalize this for contingency tables? We'll split the training corpus into two halves. We use 2 years of the AP News. And now we'll count in the first half DF for all the words in the vocabulary, including the words that didn't appear. And we group the words in the bins by DF, and let N sub DF denote the number of words in the DF bin. And then use the second half of the training corpus to compute the aggregates values of all those contingency tables for all the words in each bin. And then let A star sub DF be the aggregate of the A cells in the DF bin over the number of things in that bin. And the same for B star, C star, D star. And then compute positive and negative adaptation just as we did before, but replace the cells of the contingency table with the smooth versions. Now, what we get is a really remarkable figure. Ignore the neighborhood for now. I'll get to that. But what I'm interested in is the history versus the prior. So the prior here depends very strongly on document frequency. And the adaptation, the positive adaptation, which I'm labeling history, is independent of the prior and absolutely huge. Okay? I thought that was a really, I mean, I believe it's true, and I believe it's not well described by many of the existing adaptive language models. In particular, the additive language model, I think, has a problem with it because, first off, as we're arguing a number of times, the positive adaptation is much, much larger than the prior, often by 2 or 3 orders of magnitude. And I don't see how to build that much dynamic range into a small cache. Secondly, the prior depends strongly on frequency, and the positive adaptation doesn't, I believe. And I don't see how to do that either. I don't see how to get the right shape, because if lambda here is anything, other than 1, it's gonna carry the shape of the prior. I just don't think we can set lambda to 1. And then this is a smaller issue. This is merely a 1 order of magnitude, but it's still something. That Noriega adapts more than John does. And I don't see how to build that in unless lambda somehow depends on the words. And so the fix is to allow lambda to depend on the word and whether or not the word is in the cache. And if you do all that, I think you end up with a case-based cache model, which is what I think you should end up with. Now, this next part is a little bit messy. Maybe you guys can help me with this. In a practical application, the history won't be the same size as the test. And I was making this very simplifying assumption. It made it easy to do some work. Now, what I'm going to do are 2 ways to try to study this question of how do these adaptation probabilities depend on the relative sizes of the history of the test. The first approach is a rather direct one, which is to consider histories of varying sizes. So instead of saying the history, I'm going to split the documents 50-50, I'll split them 5-95 or 10-90 or 25-75 or so on. The second approach is to introduce a second method for estimating the adaptation that doesn't make any assumptions about the size of the history, and then conclude that this method gives me estimates of positive adaptation that are not very different from the first method. And therefore, I don't think the size of the history is that critical. This method will show that, the first one will show that the breaking them in different sizes does a systematic change to the shifting the curves up and down somewhat, but doesn't change the shape and doesn't change the basic finding that the positive adaptation is orders of magnitude different than the prior. So these are plots kind of like we had before, except that now what I've got is, this is document frequency on a log scale. Here you see the prior, the neighborhood, which I haven't mentioned yet, and then the history. That's for 5% of the document being in the history and 95 in the test. This is for the reverse, 95 in the history and 5 in the test. And you see different cells around here. What happens is, as you change the relative size of the history and the test, the plots shift up and down a little bit. But the basic observation that the history is flat and the prior is not, this quantization is introduced by a simplifying assumption in the code. It's not true. It's just an artifact of how I counted it. But basically, the prior does this very strong dependency on the document frequency, and the histories shift up and down, but they're flat. This plot may show it a little more clearly. And what I did here is just show the history, the positive adaptation as the, so the top curve here, this is with 10% of the document in the history and 90% in the test. And this is with 90% in the history and 10% in the test. And what you see in all of these cases is that the history is basically, I mean, this positive adaptation is basically flat over these frequency ranges, right? But it shifts up and down, and basically the positive adaptation falls as the size of the test decreases. Now, it isn't a linear relationship, but that intuition, I think, makes some sense. That if the test region is smaller, these probabilities drop. Now, I'm not going to work on exactly how to fit this, but just mention that in any case, the shape maintains the same, and these don't change by that much. You know, there's maybe a factor of 2 here. And since I'm really trying to get orders of magnitude, not factors of 2, I'm going to push this off for future work. Now, let me go to method 2, which is a totally different method of estimating positive adaptation. And what I'm going to do in my method 2 is to say that the positive adaptation is what's the probability of seeing 2 or more instances of hostages anywhere in the document, not just in the test, given that I've already seen 1 or more. And so this I'm going to make as just the ratio of 2 empirical quantities, which I'll call df sub 2 and df sub 1. df sub j is the number of documents with j or more instances of w. So this is just how many documents did I see in my training corpus with 2 or more instances of this word, over how many documents did I see with 1 or more instances of this word. And what I'm going to show is that the 2 methods of adaptation are quite close. That is, they're quite similar shapes, and they're within a factor of 2, roughly, of one another. And this suggests, this method, too, it doesn't really say anything about how large the history is, or it kind of averages over all histories. And so it suggests that this positive adaptation isn't all that sensitive to the sizes of the history, factors of 2 or so, rather than orders of magnitude. And now method 2 has some advantages and some disadvantages. It's straightforward how to generalize this method to ask what's the probability of seeing 3 or more, given I've seen 2 or more. But that's a nice thing. So I can say, what are the chances of seeing the 3rd, the 4th, the 5th instance? The thing I don't know how to do with this method is how to talk about negative adaptation. But my method of dealing with that is to use method 1 for negative adaptation. Now, here's the first of a bunch of arguments that the 2 methods are kind of similar. These are those same words we talked about before. Out here, we've got Noriega and Escobar, and down here, we have our function words. And these are the probability of positive adaptation by method 2 and the probability of positive adaptation by method 1. There's one outlier up there, which was an Aristide that should have been smoothed and wasn't, and came out with a probability of 1 when it isn't. But other than that, the 2 methods are quite close by eyeballing it. And this gives slightly better look at the same thing, where what I'm showing here is document frequency for low frequencies between 0 and 300. And over here, I show the ratio of the positive adaptation by method 2 to the positive adaptation by method 1. And they're well within a factor of 2, and quite a bit closer than that. I'm looking at differences of between 1 and 1.1 ratios, so that method 2 is coming out with slightly larger estimates than method 1. Now, here what I do is to show the plot. This plot looks a little like we had with method 1, but these are document frequencies from 1 year of the AP News. Then we got smooth versions from another year by, and so this is the prior, which is what's the probability of seeing 1 or more instances of this word. And those are labeled with 1s. The positive adaptations labeled with 2s, and the third instance is labeled with 3s. And what you can see is that the adaptation cases are flat. They're independent of frequency. And they're much, much larger than the prior, not even close. Let's see. This is to say that this is showing the same plot. The top plot is the same as what we saw before. The bottom plot is just to zoom in on here I've got a linear axis as opposed to a log axis, and I'm zooming in on the low frequencies here, and you can see that the 2s and the 3s are pretty flat. If anything, the 3s seem to be dropping. Now, this is a comparison with what you would expect. The top plot is what we observed by method 2, and the bottom plot is an attempt to synthesize the same stuff with a Poisson. And the interesting thing you see is that with the Poisson, the first instance, the second instance, and the third instance all depend strongly on frequency. They're all kind of close to one another, right? And they're ordered, 1 is more likely than 2, which is more likely than 3, which is just the reverse of what we see here. That is, the third instance, given that I've seen 2, the third instance is not all that implausible. Whereas by a Poisson, given I've seen 2, the third one is about the same as when I didn't have that given. And to anything, the slight details, it's a little bit less. Now let me talk about neighborhoods. The motivation here is that if the history mentions a bunch of words that are related to, say, the peace process, but doesn't actually mention the word peace, I would expect the same types of things to happen. That is, that the likelihood of peace, spelled this way, should go way up, related to other ways of spelling those acoustics. So we'll imagine the same context, but this context does not mention the word peace anywhere. I still want this likelihood of X to go up. So what I'm going to do now is to partition the vocabulary into 3 classes. Before we just had 2. You're either in the history or you weren't. Now we've got you're in the history, you're near the history, or you're not. And the neighborhood I'll define as, say, take the history, use it as an information retrieval query, find me K documents that are in my library that are close to it in an IR sense, and then use the words from those documents, but subtract out the words that are in the history, right? Because the intuition I've got here is that being in the history is better than being near the history, which is better than not being either, all right? And I'm going to, unlike the work that was done here, I'm going to be using nearest neighbors as opposed to some kind of clustering. Now, so what we had before for this word peace was a 2-by-2 contingency table. Now what I've got is I've broken out that bottom line into 2 more lines, so I have a 3-by-2 contingency table in which there were, you know, well, I think it's straightforward. And going through these, I can define in rather straightforward sense the probability being in the test portion given in the history is the same as it was before, but now we've broken out the not history into 2 cases. You're near the history or you're not. And if you're near the history, I broke out the cell C into E and G, and the cell D into F and H. And so then the negative adaptation is broken up into these 2 cases. And now I just bring up that slide we saw before. This is exactly the same slide. And what I want to argue is that the history is really the best. It's way up there. The prior is sort of in Never Never Land. And the neighborhood is somewhere in between. And of course, it depends a lot on exactly how you define neighborhood. And I was very fast and loose about that. And I'll get a little bit into that in a moment. But let me go through just a few of these words. I like to look at specific words. And we compare Kennedy to accept, which we said before are sort of equally frequent, but Kennedy is more adaptive. And peace spelled one way and peace spelled another way, which I want to say is somewhat the same. This is a more compelling case than this one. And what you see here is that the history in case of Kennedy is quite a bit larger than the prior. It's also, well, let me make the other comparison. The history is much larger than the neighborhood, and the neighborhood is much larger than otherwise. Whereas with accept, you see the same relationship, but it's not as dramatic. Now, one thing to note is that the relationship between the neighborhood and the prior, they're often kind of comparable, depending on how you define neighborhood and depending on the word. Peace and peace, I want to say, is somewhat the same relationship, that this history is quite a bit larger than the neighborhood, which is quite a bit larger than otherwise, which is less extreme here. I think on this case, I'm on more thin ice. Now, how do we pick this size of the neighborhood? What do I mean by K nearest neighbors? How does it vary on K? Now, this is a little messy, too, and I think this is an area where we could do better. What I used was a simple, you could say TF-IDF, but I just used IDF, Information Retrieval search engine. But then when I've got some number of documents that are near, I rank all my documents by how close they are to this history. And then I could choose any K, and I looked at Ks between 1 and 100. And here are all the cells in the contingency table, A through H. Here I show the ratios of, this is the neighborhood probability, and this is the otherwise probability. And what I want to do, I think, is to maximize this and minimize that. And I just looked at the ratios here and found that 7 or 10 was kind of a good place. And that's what I went with.
What is K?
K is how many documents. So I've rank ordered all my documents by how close they are to the history. And now I want to say, how far down this rank ordering list do I go to include words in my neighborhood? If I made K 1,000,000, then there would be no distinction. Yes?
Do you take all the words or just let you have a stop?
I take them all. There obviously are better things to do. I think this is meant to be suggestive of an approach to how to go than the last word. All right. So the idea is that you would do some kind of nearest neighbors to find some documents that are near the history. Then you would pick words out of those neighbors by some way and deem them to be in the neighborhood. You probably might even want to stratify and say there are different classes of neighborness. There are really close neighbors and not so close neighbors. And I could probably support a dozen bins here of the best neighbors and the worst neighbors by how many documents they were in and what kind of words they were and so on. Now, in previous work with Bill Gale, we talked about enhanced smoothing methods. And in that context, what we were talking about is the standard methods of smoothing bin by a single variable, like frequency or DF. And an enhanced method, I bin by 2 or more variables. In that work, we used the joint frequency of a bigram and the marginal probabilities of the bigram. And found that the 2 variables gave us some leverage. Here, I'll use df sub 1 and df sub 2 for binning. And what I've shown here is that for words that occurred 5 times in 5 different documents, there are 6 possibilities for how many df2 values they could have. And what you see is that there's a big difference in how much they adapt based on this distinction. So that the words that occurred 5 times in just 1 document and never in 2 or more documents, that is, they all occurred once in 5 different documents, that's sort of like Poisson distributed, and those things hardly adapt at all. Whereas if all of them occurred, not only they occurred 5 times in 5 different documents and always repeated, then they really adapt. They've got a huge chance of appearing multiple times. And this is the adaptation by method 1 and the adaptation by method 2, and I want to argue that these things are well within a factor of 2 of one another. And this is the same thing for words that occurred in 6 documents, and shows the same pattern. That is, the more they repeat, the more they adapt. Now, I did a little bit of experimental results. This is very preliminary and maybe not as promising as I had hoped. But we measured the likelihood of the probability using the proposed method to a baseline probability for each word type. And the proposed method is that I'm going to make 3 different distinctions. Either the word's in the history, it's in the neighborhood, or it's not. And I'm going to test the words in the test portion of an unknown document based on this distinction of the first half of the document. The baseline method just uses this simple method. And the findings are that we get a small but not great information gain in terms of bits per word. There are a bunch of documents. There are some non-trivial number of documents that gain a huge amount. And there are many more big winners than big losers. And what I think I can do is I think there are ways to improve the method to fix this. And this is showing that there's real promise. Let me show a QQ plot of the documents. This portion down in here is the reason why we're not seeing the overall average changing, which is that you have to be in the sort of 2 orders of standard deviation out of the normal test document before you get a huge improvement. Up here is the huge improvement. In here, it's sort of saying the method down here for the majority of documents doesn't make a lot of difference. But for a few documents, it makes a huge difference. Now, if you subjectively look at the big winners and the big losers, you see these kinds of patterns. The examples of big winners that I found were lists of major cities and their temperatures. If you see a bunch of cities in the first half of the document, you can guess what the cities in the second half of the document are. Lists of major currencies and their prices, lists of commodities and their prices. I suspect it would be lists of congressmen and how they voted. These would be very predictable type things. The examples of big losers are, there's a bunch of documents that summarize the major stories of the day, the week, the year, where the first half of the story is about one story, and the second half of the story is on a totally different subject.
Loser is something where your method
did worse than the baseline.
It does worse when applied to what?
So
I mean,
take a document.
What is the
So,
Goodness criteria.
oh, yeah. Here. So the score here is the sum over the word types in the document of what probability I would assign to them versus what probability you would get from this. And in this, what generally happens is if the history is misleading, then this does worse than this for what the scores are. So if the general property is that this thing will cause if the first half of the document is about one thing and the second half of the document is about something totally different, then all the words in the second half I'm going to score with negative adaptation. And the negative adaptation is worse than the prior. So if the bulk of the words in the test portion are getting negatively adapted, I'm doing worse. And so what a big loser is when all the words, or most of the words in the test portion are getting negative adaptation scores. And when does that happen? Oh boy, how do you manage this? There. Okay. That happens when, like for these summary stories, where the story consists of a one-line sentence about each of the major stories of the day. The first half of the story is on one set of stories, and the second half of the story is on another set of stories. The second half of the story will all those words will get negative adaptation scores. They all do worse than the baseline. So another thing that happens is that some number of our stories were garbled in transmission, so the two stories were concatenated together without an end of document token. And in this case, the first half of the story is on a totally different subject than the second half. And I will score the second half as negative adaptation. Now, the big winners are when the test is very predictable from the history, and the big losers are when the history is misleading. And the suggestion for future work is to do something like Marty Hirsch did, or what the folks here did, which is to try to guess the topic, or to guess whether the topic is changing in midstream. So that is, if the neighborhood is on the first half of the document is different than the neighborhood on the second half of the document, then don't use the adaptation. Now, one more thing that's sort of similar is that most of these contingency matrices are symmetric. So that is A is the number of stories that mention this word in both the history and the test. B is how many mention it in one but not the other. And C is how many mention it in the other but not the one. And D is how many mention it in neither. And I'm saying the B and C cells are usually kind of comparable. And that would be true if the assumption that the history and the test are from the same distribution is correct. Right? However, there are some notable words for which the B cell is much, much bigger than the C cell. So most of the AP stories start out with a little header that includes the token AP. And this token is not repeated in the test. Right? They also start out with the names of major cities. And those cities are less likely to be repeated in the test. They also, when they introduce the main characters of the story, they often explain who they are, like spokesman for this, that, and the other thing. And so there are certain words that are asymmetric. These words also, I'm going to argue, are going to screw up the method that I described earlier. And one could imagine ways to correct for this. I'm not going to do that now because I think I'm close to out of time and I didn't do all the work. But let me start concluding. What I've done here is to describe two methods for estimating positive adaptation. One is this method where I split the documents into test and history and count what's the probability of being in the test given that you are in the history. The other one is to count how many times I saw it 2 or more times given I saw it 1 or more times. Both methods produce similar results, well within a factor of 2, and as opposed to the orders of magnitude that we see the separation these often produce. Then I introduced this I think, novel way of thinking about similar words, synonyms, collocations, and so on, by relating neighborhood to information retrieval notions of query expansion. We talked about cache-based models, and I divided them into two types, which I call additive and case-based. And we agree with Fred that the case-based is better than the additive, that the combination rule should depend on what the word is, that is saying the adaptation is lexical. That's probably less than an order of magnitude, but it's something. And that the word should depend on its presence or absence in the cache, that is many orders of magnitude. And that's why you need to do it, but also because it has a different shape, and I don't see how to get that shape by an additive model. Now, I think this work opens more questions than it answers, so there's a lot of future work. One idea that we mentioned earlier is to stratify the neighborhood so that not all neighbors are equally good. Good neighbors are words that appear lots of times in lots of documents near the history and not hardly anywhere else. Bad neighbors appear almost everywhere, hardly elsewhere and not there. You could imagine having k degrees of good neighborness and split out that neighborhood cell into case rows. We split documents into history and test. You could do the same for other linguistic units like paragraphs and sentences, and I suspect you would discover something. I mentioned earlier, these are both issues about when this method goes awry is when the history is not representative of the test. And you could build models to try to measure whether or not that's true and correct for that. And there's some literature on that, and this is perhaps another way of doing it. Or maybe this is really equivalent to those. Now, here's a very radical idea, and I've run this by some diehard IR people, and they absolutely reject it, but I still think it's a good idea, which is a totally unsupervised approach to information retrieval research. What we did is we defined neighborhood to be a query expansion of the history using some IR method. And what you could do is to search a space of possible IR methods and find the one that gives you the best prediction of the test given the neighborhood using some criterion of goodness. Now, this is the kind of thing that I could imagine you guys here doing and IR literature would never do. And however, a much less radical thing is to do the same thing but call it an unsupervised approach to language modeling. And that, I think, is a perfectly plausible thing to do. Now those I would say put in the list of sort of thesis topics. These are more like good homework problems. Maybe that's a bit exaggeration, but I'd like to have a better theory of document length. Exactly how does this probability of positive adaptation decrease with the size of the test? I don't believe it's linear, and I don't quite know what it is, but I have the feeling that that's not a hard problem. And also, I'd like to have a better theory of neighborhood size, that my intuition is the size of the neighborhood should grow inversely with the size of the history. But I certainly don't have that as a property of anything I showed. Negative adaptation, we talked about how to use method 2 to give me positive adaptation, but I don't know how to generalize that to give me a model of negative adaptation. There's some obvious hokey things you could do, but maybe you could show the hokey things are equivalent to the method 1 negative adaptation. So that's what I had to say. Yeah?
You said that if there was a radical topic shift within a document in this case, that the scores were bad.
Yes.
Does it work the other way? Does the bad score also indicate a radical topic shift, usually?
I don't know. Of course, I don't have a labeled corpus with radical topic shifts, but I guess what I could do is to take a random sample of guys with good scores and bad scores and then hand them to human judges and ask them, is the first half about the same thing as the second half? I guess my intuitive judgment from having read some of these is I would say yes, that's more likely than not. and that when to the extent that this is not producing stunning results, it's because the characterization of the problem is wrong. That is, the document, the first half is representative of the same thing as the second half. But you know, that's speculation. I should check that. That's a good question.
Right. So I'm working in this topic-based novelty detection group, right? So we're,
Yes.
when you're interested in detecting new stuff.
Right.
So if a radical shift is a form of new stuff, it might be an interesting way to look at it.
Yeah.
In
No,
that case, it's across documents rather than within documents.
right. I mean, it's somewhat like the last bit of future work, which says, take this measure and spin it on its head to solve another problem. Sure. Yeah.
So, if a cache consisted of the last, say, 100 words or whatever, then this radical shift then would not be as much of a problem, right? Because once you move across, you got totally new cache, doing the same thing.
Yeah, but then the flip side of it is then the cache wouldn't have enough dynamic range. I have a feeling there's a sort of no free lunch theorem here about, you know, there's stuff with, you can't have time and frequency resolution at the same time. I don't know how to make this precise, but I suspect there's something like that here. You can't get this dynamic range and capture topic shifts simultaneously. Maybe Fred knows how.
In the cache language model that we had at IBM, the best history was 200 words. And if you made it longer, it got worse. If you made it shorter, it got worse. So, I mean, of course, these were particular type of documents. These were IBM Office correspondence. But
Right.
well, you know, I don't know. But the point is that obviously, in any case, the question is not your measures. If it's a language model, does it reduce the error rate? That's the question.
Well,
Not whether you know your measure is no better than perplexity, and we know that's a pretty bad measure.
well, this
except
is
that there's no
basically
better one.
perplexity. It's
Right,
relative
right,
perplexity,
exactly.
right? It's how many bits better did I get it? I did get it better than the baseline. The baseline isn't a very good baseline, but it's something. What I think I'm saying here, though, is that the size of the cache probably should depend on your estimate of how consistent the history is with the test, and also what the words are involved. So it sort of says there are different bandwidth filters for different purposes, and that a single bandwidth is probably not optimal for everything. Right? Now, I think this shows plausibility for that position. It doesn't nail it.
Well, I like the neighborhood idea because,
Yeah.
for instance, in triggers, which is what Rani Rosenfeld does, right?
Yeah.
We almost get no gain except for repetition.
Right. And this is saying,
Yeah, but maybe you would get, maybe your neighborhood does a little better.
yeah, I think this shows plausibility that it ought to, yeah. As long as the document doesn't change topics totally in midstream. Yeah.
So if I understood correctly, so you're just predicting whether or not a word is heard in the last half of it.
That's right. I'm not going to count how many times or anything like that.
Look at all, and you might also predict the frequency of words that are maybe.
Well, that's kind of what the 2 and the 3 line are about. The 3 is to say that if it occurred twice, would it occur 3 times? And then you could say if it occurred 3 times, would it occur 4 times? If it occurred 4, will it occur 5? And I'm saying it's the same argument. It just gets more extreme. So those would probably start to show me more leverage. That is, here I was sort of focusing on a simple case, but a somewhat harder case. Yeah. I mean, it's a good thing to look at. I haven't done it except to show you those plots that showed that it was getting more extreme, not less. Yeah. Yeah.
I wonder if any of this is an artifact of news report. You're taking as your history the beginning of the story and
Right.
you're predicting words and later on.
Certainly, the asymmetry that I went for was based on my knowledge of the weirdness of AP News. That AP News starts with this lead, and the lead has the name of a city in it, and Washington is one of the big ones, but Tokyo's up there.
I wonder if that's also one of the reasons you get repetition, because in the first paragraph they summarize the story, and then there's this pyramid structure they're supposed to use in journalism, and so then they give you more and more details.
Yeah.
So they're almost guaranteed to repeat those
Well, this is very easy to test, and I think that all the literature on cache-based models, and also that the little factoid I mentioned about Japanese keyboards, suggests that repetition is really huge, and probably doesn't depend on the newspaper style. The newspaper style does influence things.
Might have come up for now.
Right. I wanted to use that because I had a huge amount that was fairly homogeneous, and I didn't have to be very careful with how I split things. I used, a year here, a year there. Most of this work I did on sort of 5 years, but I actually have 10. So there's plenty more to go test hypotheses on. I don't have to worry about running out. We do have quite a bit of other data, and I could check, to see whether the Brown Corpus or the Bible or Harper and Row books or whatever follow the same pattern. But my knowledge in looking at the Bible is written like with poetry. It uses unbelievably long ngrams that are repeated verbatim. So that the repetition there is also quite prevalent, but also you might say, well, maybe the Bible isn't representative of general contemporary language. But, yeah.
Well, I'm just making a remark that certainly cache works in IBM Office Correspondence,
Yeah.
and that's written by class, right? And so there is no rule like that to make it easy for people to read. These people don't know how to write, and they write each other, and they repeat.
Right.
So,
Now, of course, in the
repetition
office correspondence, you might also expect a certain amount of verbatim because people plagiarize from one another, like they forward the same comments on.
No,
and-
this is, well, okay, this is the early 70s. I mean,
Oh,
there
before
wasn't
the
much-
repeat key was very easy to use.
There was not much email then,
Right.
and so, right.
This is actually a clarification on what Stan asked. So if they say document that had 100 tokens, that's the second half of it that you mentioned, but it had only 30 types, then how many W's do you count?
I only counted types,
30.
30.
Okay. So
And I also ignored a bunch, like if the hokey measures that I used for the baseline gave me 1 or 0, I ignored the type.
the question is, have you done anything at all with actually counting them as many times as well? Because that would then start getting towards perplexity. Because
Well,
that would be a unigram perplexity.
Yeah, but what I really don't want to do is to say that this, see, here's what I'm worried about. If Kennedy occurred 10 times in a document, and I give a likelihood ratio by my method of 1,000 to 1, I don't want to say that now I take that 1,000 to 1 and raise it to the 10th power, because that's absurd. I would get a fantastic score for my method by doing that, but
In fact, I expect that you won't, because there are a lot of these other words which will pull your average down, such as the very frequently one, which is
yeah. But you see, what I really tried to do very hard here is to avoid that independence assumption. What I would want to do for 10 to 1 is more what I said in the previous question, which is to estimate what's the probability of getting 10 or more instances of this given I got 9 or more, rather than taking what I got for 2 or more given 1 or more and raise that to the 10th power.
I agree with your analysis, because if you're proposing this as a two language model, you really do want to assign a probability of every word that comes out, every token that comes out.
No, you see,
Counts as if you do in each token.
no, because if you do that, you're introducing a very inappropriate independence assumption.
Well,
I mean, obviously you'd like to have an online procedure, but I think you can.
The assumption is an artifact of your model. Nobody says you have to introduce it, but you're doing it anyway.
Well, no, I don't have any independence
No, so
assumption.
what I'm saying is the comparison would be with an n-gram model. Say baseline would be a 4, 3, 5, whatever n-gram
Yeah.
you say now. And then I'm sort of going out on a limb and saying
Right.
how's it mathematically.
Well, I think if you introduce inappropriate independence assumptions, you get what you deserve. But that's my opinion.
On the other hand, what I'm saying is I'm questioning the value of these conclusions, because after
Yeah.
all, Kennedy appears only twice and you get a ratio of 20 to 1. All the other words which appear a million times, you don't gain anything on them. So
Well-
what is the benefit of doing this in language models?
The aggregate number of words that don't occur much is huge. But, you know, that is, you know, sure, there's a couple of words that occur very frequently, and then there's a whole bunch that don't. You know, you know, I think that what you say is, you know, I disagree, but you know, we can go look at it. Yeah.
Well, I think on the other hand, he has a point which he isn't making, I don't know why, that the rare words are important for knowing what the contents of the document is, and you really and so if you measure things by our stupid error rate, then you're right, it won't have any effect. But if it's important that this talk is about Kennedy.
I'm acting adversarial, but I'm actually an advocate of all these methods.
And
you know that. And what I'm trying to get to eventually is that what happens is that the result, if you count it the right way, is not as dramatic, but on the other hand, there's little bit that's significant. And that's what really counts.
All right. So in information retrieval, they take all the words you would give huge weight to and they call them stop words. And they ignore them completely for the reasons Fred's making. In this field, we use a measure of perplexity, which puts all its weight on the function words. Maybe the measure is not the right measure.
The answer I was hoping you'd give me is that even if you did it that way, all the gains would look smaller, but this is where the action is. And so this is
All right.
I would say, I think from my experience in playing around with it, I think that that's true, that we did some cache modeling with not rare words in terms of frequency, but more in a lexical base, not as sophisticated as what you did, but it was better than doing frequency-based rare words, which is better than doing everything. And so I think the stuff you're saying is very relevant to language modeling.
In fact, there is more to it because June has done more to it than that. For instance, one of the things that happens is you think that Noriega and Escobar are really very nice, but if you start looking into ngrams, given Pablo or given Manuel, they're not all that unpredictable at all. And so what happens is you start seeing these interactions. That's another reason why this unigram type of analysis is a bit misleading. The comparison should really be with a ngram model working without this topic information, whatever it is. But it turns out that you alluded to this notion of making this lambda depend on the word and all that in the cache model. So what June did is he did this using maximum entropy and get both the ngrams and the topic constraints. And it turns out all you really need are these topic unigrams because they interact nicely with the ngrams.
Yeah, you kind of make an independence assumption there that I bet would be okay. Yeah.
So let's have lunch.
Thank you.